Mathematics Community and Algebra Research Group of Faculty of Mathematics and Science ITB proudly present Mathematics Webinar on September 30 until October 2, inviting international and competent speakers Artur Kornilowicz, PhD from University of Białystok, Poland, Dr. Shakir Ali from Aligarh Muslim University, India, Professor Tomasz Brzezinski from Swansea University, UK. Register yourself to this link. Live on Mathematics ITB YouTube channel. Mathematics Community and Algebra Research Group of Faculty of Mathematics and Science ITB proudly present Mathematics Webinar on September 30 until October 2, inviting international and competent speakers Artur Kornilowicz, PhD from University of Białystok, Poland, Dr. Shakir Ali from Aligarh Muslim University, India, Professor Tomasz Brzezinski from Swansea University, UK. Register yourself to this link. Live on Mathematics ITB YouTube channel.
Established in 1920 with the name Technische Hogeschool, Institut Teknologi Bandung, or ITB for short, is the oldest technical university in Indonesia. Located in Bandung City, West Java, Indonesia, ITB now has 12 faculties or schools with 49 bachelor study programs, 52 master's programs, 27 doctor's programs, and 2 professional programs. ITB's vision is to be an outstanding, distinguished, independent, and internationally recognized university that leads changes towards welfare improvement of Indonesian nations and the world.
It is great honor to meet all of you. I'm Kadasa Suryadi, Rector of Institut Teknologi Bandung. Welcome to ITB. ITB has declared to move from research university toward entrepreneurial university. It is marked by 3 key performance indicators: excellent in teaching and learning, excellent in research, and excellent in innovation and entrepreneurship.
Excellence in teaching and learning's progress is marked with an accreditation that is earned on a continuous basis. 34 study programs of ITB have received accreditation from international accreditation boards. More international accreditation boards will follow. As one of Indonesia's centers of research, ITB has produced a wide range of research from 5 centers of excellence. These research projects result in excellent innovations that are expected to compete in national and international markets, which will certainly make an impact on the economy, improving it significantly. ITB creates innovation that departs from problems in industry and communities. Research is conducted in order to deliver the best solution that will enhance production quality and resource efficiency through support of technology. ITB also continues to collaborate and build synergy with the government. Industry, and other higher education institutions. This will lead to the creation of new technology. This new technology is expected to enhance the economic prosperity of Indonesia in general. One way to make this happen is through the development of science and technoparks in various locations. ITB Innovation Park in Ganesha, ITB Innovation Park in Gede Bagay, and STP Vasanta Innovation Park in Bekasi. By upholding three pillars of education that comprise education, research, and community service, Institut Teknologi Bandung will consistently produce excellent human resources for a better Indonesia.
Good morning, Professor.
Good morning, good afternoon.
It's still early morning there, right?
Well, in my place, yes.
Yeah. Yeah, maybe we will wait for 2 or 3 minutes so the participant will join the meeting.
Okay, yeah, sure.
Yeah. Okay. Okay, Professor, maybe while waiting, This algebra seminar is held 3 days from 30 September. So our first speaker is from University of Bielefeld, Poland. I read from your CV, you're also teaching on that university, right?
Well, yes, actually, so it's also my colleague, yes, from the.
Yeah, Professor Colonel Lewis on the first day. It's very interesting about Miser.
Yeah, it is a system for proving or checking the correctness of proof of theorems and formalization of mathematics, yes.
Yeah. And also yesterday we have Professor Shakir Ali from India.
Mm-hmm.
And then today, you're our last speaker. We save the best for the last, maybe.
But let's hope not.
Yeah. In this meeting, there is Dr. Gantina Rahma Putri, the head of the committee of this event, and also Professor Irawati. She's my supervisor actually on my master degree.
Hello.
Okay, and yeah, maybe some of them is trying to go to join this meeting. So perhaps okay. Actually, Professor, about yeah, it's maybe about the scholarship information that you've shared to me. I decided not to apply because
I noticed because the deadline is, I think the deadline is passed now, so it's
yeah, but actually I sent an email to PGR scholarship, and they replied to me that it is not applicable for international students, and the available scholarship will always be written in the Swansea scholarship website. So I cannot apply. But I really thank you for the information.
You're welcome. If there is any, if you are still interested and there is any funding for scholarships, I can give you information, let you know.
Yeah, thank you.
There is an opportunity.
Yeah. Actually, in Indonesia, Indonesia has a scholarship program too to go abroad, but Swansea University is not in the list. University that can be covered by them. So yeah, we have to. Oh, Fitri is still waiting. Yeah. Yeah, from Professor Irawati. Yeah, that's right. Maybe I will try again next time.
And the university in Białystok, is it on the list? The university.
If I'm not mistaken, no, it's not in the list. Yeah, but if I'm not mistaken, next year, Swansea University will be in the list. So maybe I will try. Yeah. Okay. Maybe we will start the seminar. Okay. Okay. Okay, ladies and gentlemen, may I have your attention, please? Our algebra seminar is about to begin. During the seminar, we kindly ask your cooperation to turn your microphone off for the conduciveness of the event. And also, if possible, we kindly ask you to turn on your camera. Okay. Yeah. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. We are really happy to welcome you again to the first day, to the last day, to the last day of the Algebra Seminar 2022. Thank you so much for attending the third day of this event. This seminar is organized by the Algebra Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, Indonesia. So I am Fitri Ferdania, will be the moderator for this event. Participants, firstly, I want to introduce the Algebra Research Group to all of you. The Algebra Research Group is one of the 5 research groups in the Department of Mathematics in the Faculty of Mathematics and Natural Sciences, ITB. This research group has 14 members, and it is led by Professor Puji Astuti Waluyo. And among the 14 members, 10 of them has PhD degree, 3 are currently in intake of a PhD program, and while 1 is still looking for scholarship for PhD study. Our research interest lies on algebra and module theory, such as hereditary, prime, and semi-prime properties. Research in this area includes research in module theory using categorical approaches, such as abelian triangulated and drive categories. We are also interested in linear algebra and matrix theories that include properties of linear and indefinite inner product basis. Some of our members are also now interested in the application of algebraic structure, encoding theory, biological problems such as DNA, and cryptography. And recently, we have expanded also our research interest to traces and graph theory with graphs constructed from the algebraic structure. And now we are conducting the annual event called Algebra Seminar 2022. Ladies and gentlemen, this year, Algebra Seminar is conducted virtually from September 30 until October 2, 2022. And the event aims at enriching our knowledge in algebra and also expanding the research network among researchers worldwide. Ranging from students to lecturer, the participants of this event is not only from Indonesia, but also from many other countries, such as India, Philippines, and Morocco. This is a 3-day event, with the first day featuring Professor Cornelowicz from the University of Białystok, Poland. He delivered a great presentation in the introduction of the interactive theorem proving called MISAR, as well as the strike demonstration of working with MISAR. And also on the second day of this event, which is yesterday, it is an honor for us to have another presentation delivered by Professor Shakir Ali from Aligarh Muslim University, India. His lecture yesterday is about the differential operators in rings. And last but not least, on the last day, we will have Professor Tomasz Brzezinski from Swansea University to deliver a lecture about traces. I think because our today's speakers, Professor Tomasz Brzezinski is already among us right now, maybe it will be precise for us if we conduct photo session first. Is it okay, Professor? Okay, yeah.
Yeah, it is fine, yeah.
Yeah, so for photo session, please turn on your camera. Maybe we will wait for a while to wait all of you to open your camera. Okay. Okay. Okay, thank you. So yeah, we still wait for you to turn on your camera if you want to join the photo session, maybe. Okay, maybe that's all. Okay, maybe Dr. Gantina, can you please help me to
Okay.
finish it?
Okay. In count of 3. 1, 2, 3. Okay, let's see the result. Yes, it's already good.
Good.
Thank
Okay.
you, Fitri.
Okay, thank you so much. Okay, yeah, thank you so much for the photo session. Yeah, okay. Yeah, dear participants, before proceeding straight to the session, firstly, let me mention some of the key rules while attending the session. For the sake of conduciveness of the event, again, every participant has to turn off their microphone, except if allowed. And also, if possible, keep your camera on during the sessions. Any questions can be written in the chat box or can be asked directly to the speaker by unmuting your microphone after being allowed by the moderator. Okay, so without any further ado, let me call again Professor Brzezinski from Swansea University that will be presenting a topic entitled On Traces. Good morning, Professor. Good afternoon from here.
Thank you very much. Thank you very much for the invitation and for the introduction.
Yeah, we're very happy to have you in this seminar.
So before I start, I heard this morning about an awful tragedy in the Western Java with the football event.
Yeah,
so I would like to express my deepest sympathy for all the victims and their families. It's an awful thing that happened there. So hopefully it will never happen. Such things will never happen again.
Yeah.
So I guess I should start sharing my screen.
But maybe before we start, I'd like to share your short resume first. Is it okay? Okay. Okay. So here it is about Professor Brzezinski. He is a professor of mathematics at Swansea University since 2005 and also at University of Białystok, Poland since 2015. Specializing in algebra, in particular studies of various algebraic structures such as rings, modules, co-rings, comodules, and Hopf algebras, non-commutative geometry, both algebraic and differential with particular stress put on symmetric aspects, category theory, and some aspects of mathematical physics, quantum groups, integrable systems, and also he is the author or co-author of a monograph and more than 100 papers written with 45 co-authors. And his most notable work is in the revival and significant development of the theory of co-rings and comodules. And also here is his educational history. On 2016, he got the state professorship from President of the Republic of Poland, habilitation from University of Lodz in 1999, PhD in mathematics from University of Cambridge, and also MSc in physics with cum laude predicate from University of Lodz. And also the next slide, maybe. Okay, here is his key publication, authored book, Co-rings and Comodules with Professor Robert Wisbauer, and also some of his articles related to his talk today, as traces, paragons, ideals, and modules, traces between braces and rings towards semi-traces, modules over traces versus modules over rings, direct sums and free modules, ideal ring extensions and traces, from pre-traces to skew braces, and also on functor between categories of modules over traces. Okay, so yeah, that's all. I can say that you are one of a big name in algebra, right? So yeah, moreover, I can say that traces are still a new topic, so perhaps our participants really want to know more about that in this lecture. So Professor, you may start your lecture now until 8:45 BST. So yeah, the time is yours then.
Okay, thank you very much. So I will start sharing screen now. Okay, so I hope you are able to see just a blank page with trusses written on it.
Yes, yes, it's visible.
Okay, so let me move this a bit. Okay, so I need to, as Petri mentioned, that so thank you very much for the very kind introduction and the invitation. And trusses are a very new subject, and I have to make a disclaimer. So you might know that the current Prime Minister of the United Kingdom is called Liz Truss. It is completely coincidental; has nothing to do with the name Truss related to this structure. So, there's nothing political or in my talk. Right. So so let me start. I mean, the trusses appeared in one of my papers in 2019-18. So they are quite a new subject. And I will first I will give you some motivation. What was my motivation in introduction them, and then step by step I will be introducing the algebraic background that is needed to define the truss, and then we look at some perhaps examples and properties. It depends how far I will manage to get. So I have in the first part I have something like 90 minutes, and then we have a break and for questions if there are any questions. And I am also happy to answer any questions during my presentation. So if you want to ask a question, you can put it on the chat. I'm watching the chat space as well. So after 2 years of teaching online with giving lectures, I'm quite adapted to looking at both the chats. I can see a comment there. Right. Okay. So motivation. So first of all, everybody knows what a ring is. So let me just remind you, the rings are basic algebraic structures, and they underline arithmetic of whole numbers or many other areas of mathematics. Functions can be made into rings, or rings of operators, a lot of basic mathematical structures, and not so basic, can be organized in terms of ring. And the basic property of the ring, or the definition, is we have a set which has a plus operation. We're making it into an abelian group, and the multiplication, which is associative. Whenever I say ring, I always mean an associative ring. I'm not really used to working non-associative structures. Often we assume that this is not only a semi-group, so not just associative operation, the multiplication, but also that it has the identity, and we have rings with identity. And the key property, so when we have two structures, two operations on one set, we would like to, excuse me, to specify how they interact one with the other. And for the rings, the key property is the distributive flow. So if we have A dot B plus C, then this is A dot B plus A dot C. And our normal convention is that first we do multiplication, then addition. One immediate consequence of this is that, so this distributive law is that if I multiply A by 0, then I will get 0. And 0 is a neutral element for addition. And if I look at the left-hand side here and replace B and C both by 0, then I will have A times 0 on left-hand side. On the right-hand side will be A times 0 plus A times 0, and then the cancellation laws, group cancellation laws, will tell us that A dot 0 is 0. Okay, and of course we also have the other distributive law on the other side. So the consequence of this is that R with a dot is not a group. It cannot be a group, well, unless we have a trivial ring consisting of one element, because 0 will not be invertible. So even if we have identity for the multiplication, then we can never find an element A for 0 such that A times 0 is 1, because it was always 0. So this is never a group. So the best we can get is that we can remove 0 from the set, and this could be group, can be group. And this, of course, happens, for example, for a field. That's the definition of a field. If we have a commutative ring with the maximal set of invertible elements, all of them except for 0, or if the ring is non-commutative, then we will have a skew field or the division ring. Okay, so the rings are a very old concept, and a typical example, as I mentioned, is the example of the arithmetic of whole numbers. Okay, z plus and multiplication. Okay, so now in some 15 years ago, the concept of a brace appeared. This was introduced in 2006 by Wolfgang Rump. And what he considered or observed that in some situations, what is useful to have is to have a set which has a structure of an abelian group, and multiplication, which is a group. The whole set B is a group, not just a set without a specific element, but the neutral element of plus, of the operation plus, but the whole set is a group. And of course, if we have these two operations, then we can't request that they are related in the usual distributive flows. So Rump discovered that there is a possible distributive flow which is slightly different. So we have a brace type distributive flow. Which looks as follows: A dot B plus C, A dot B minus A plus A dot C. And if you have this kind of distributive flow, so with this correction here, minus A, then nothing prevents dot operation to be a group operation, multiplication to be a group operation. And why is that? Because you can find just by the similar arguments as before that with this structure, the neutral element for the addition must be equal to the neutral element of the multiplication. So when the neutral elements coincide, then, and you request this, well, actually this follows from this distributive flow. So I should say this implies that 0 is equal to 1. And of course, we also have perhaps I should mention this on the other side. If we have a two-sided brace. So it's called two-sided brace. C dot A. Then 0 is equal to 1. It follows just from one-sided property, one-sided distributivity. Now, why this strange structure appears? Well, it's related to radical rings. So a particular class of rings, and to the new algebra. Well, it's algebraic it's not an algebraic, but there is an important equation in physics, which is known as the Young-Baxter equation. Which was introduced by Young in the 1960s in the quantum field theory, so in the physics of elementary interactions of elementary particles. And then it's more or less in the same time it appeared in the work of Baxter on so-called integrable systems, or statistical models in physics. And the Young-Baxter equation then in the 1980s suddenly became, well, it was work of Drinfeld and Jimbo, who realized that there is a particular algebraic structure behind it, which is that of a quasi-triangular Hopf algebra, which Drinfeld called quantum groups, and this started interest in quantum groups, which is and revival of Hopf algebra theory, which is relevant to this day. And more or less, well, in the beginning of the 90s, when it became quite apparent that Young-Baxter equation is an exciting equation, an important equation in physics, one way of finding a solution to this equation was to reduce it to a set theoretic equation. It's a linear equation. It's an equation for matrices, a matrix equation, the Young-Baxter equation. But you can write the same equation for the basis elements for your vector spaces, and then everything reduces to operations on elements of a basis, which leads to that's operations on sets, functions on sets. And we can write a similar equation for sets, and this is so-called set theoretic Young-Baxter equation. And what Rumb discovered was that one-sided braces describe a wide class of solutions of the set theoretic Young-Baxter equation. Okay, so there are two interesting, very simple and very similar algebraic structures, rings and braces. Excuse me. And the question that I try to ask and understand is, what do they have in common? Or in other words, is there an algebraic structure which is equally simple as these two, which combines them both? So is there an algebraic structure which unifies rings with braces? Okay, so the answer is yes, it is, and these are trusses. But to get to this answer and to realize what is the best environment for all of this is to change a little bit our perspective. We are normally used to binary operations such as addition, multiplication, take two inputs and get one output. But it turns out that the proper environment for unification of braces and rings involves ternary operations. So the operations in which we take three inputs and get one output. And in particular, the important structure here is that of a heap. So part 2 is about heaps. Right, so the history of heaps goes back nearly 100 years. So that's a work of Prefer, I think in 26. Look, I think it was 26, and Baer approximately around 30. So what they realized, first Prefer, then Baer, was that you can write axioms of a group or define a group replacing, well, in group we have three operations. The definition of a group, we have three operations. A binary operation, which is a group operation. Then there is a niller operation, the selection of the neutral element. So we have to find the neutral element. So from the universal algebra point of view, this is a niller operation, the operation with 0 input and 1 output. And also we have a unary operation, so operation which reverses the elements. So for the inverse operation, we take an element and assign to it its inverse. So 1 input, 1 output, that's why unary. So we have 3 operations, but it turns out that we can combine all of 3 just into one and write axioms just for one operation. And this operation, well, prefer called Schar in German, which is the same as Herd. Then the system was reintroduced by Ukrainian mathematician Shushkevich in the 1940s, and he called it, well, in Russian, Gruda, which is same as heap in English. So the terminology is perhaps most common terminology is heap, but you can also find the name Herd for this structure, H-E-R-D. Or if you look in the algebraic geometry terminology, then you might find terminology torsor. And this is, the torsors were studied by Grothendieck in the 1960s, introduced independently of the work of algebraists. So what is a herd or a heap? So a heap is a set H with ternary operation it's called chi, H to H. Let's see some questions in the chat. Okay, just comments. Right. So I will write for the ternary operation, I will use notation a square bracket. So the triple ABC is sent to the square bracket ABC, which satisfies 2 or 3, depends how you count them, axioms, so such that first chi is associative. Sometimes people say quasi-associative. So what I understand by this, or what Prefer were understood by this, if you take 5 elements, A, B, C, D, E, okay, then you can group them into brackets of 3 in 3 different ways. So one way is this one, okay. Another one way is A, B, C, D, E, is this one. Okay, so first operate on the first 3, and then this will produce 1 element, and then we can operate on the remaining 3, or they leave the first 2 untouched, and then operate on the CDE, the remaining 3 ones. And the condition is that these have to be equal. There is a third possibility when we place the square bracket inside bracket in the middle. But this, as you will see, if I requested that equality here, then there will be a contradiction. So that's why this is not requested. So we have the associativity law, means that if you shift the bracket inside the bracket by 2, you get the same answer. And so chi satisfies the Maltsev identities, so-called Maltsev identities. And this means that if two elements meet, so BAA, two possible meetings of the element A, then as the answer, we get the second element. Okay, so if two elements coincide, two consecutive elements coincide, then everything reduces to the third element. An immediate consequence of this is that if I take the triple operation on three times on the same element, so A, this will be an A as the answer, which means that it's an idempotent operation. Okay, so that's the definition of a heap, or a head, or a torsor. And just like in the case of groups, we have groups and we have abelian groups. Abelians are the ones that the group operation is commutative. The same applies to heaps. So a heap is said to be abelian if ABC is CBA. So we swap the outer elements, keeping the middle one in unchanged. Okay, so that's a concept of a heap and abelian heap. I will, in a couple of minutes, I will give you examples of heaps so that you will see that it's quite a natural structure. One thing perhaps that I should also mention is what is the homomorphism of heaps. Okay, so the homomorphism of heaps. So if you have one heap H chi, H prime chi prime, then the homomorphism of heaps is a function from H to H prime, which preserves operations, so such that f of the bracket A, B, C, okay, so this bracket is just chi applies to A, B, C. Is the same as the bracket of f of A, f of B, f of C. Okay, so that's chi prime applied to f of A, f of B, f of C. And one more thing that I should stress here is that I didn't say, I should have said it, that all these axioms are for all A, B, C, D, E. Okay, which is a significant difference if you think about the definition of a group. We have an existential axiom there. There exists an element which satisfies certain properties. And also for the inverse, there is an existence required. Okay, so for every element X, there exists an element X inverse such that satisfies certain properties. Okay, in the definition of a heap, only the universal axiom is used, so that's for all, no restrictions. And this will lead me to examples. Okay, so the simplest example of all is empty set. Okay, so if there are no elements in the set, then any axioms for all elements is satisfied because there are no elements there. So there is a heap structure on an empty set. There is a unique function from the Cartesian triple of the empty set, which is an empty set into an empty set. Okay, so that's the first example, which is sort of trivial. However, it creates sometimes problems. So often I will assume that my heaps are not empty.
Professor Brzezinski,
Yes.
sorry for interruption in the middle way.
That's
Just
right.
just go the first previous slide, because just I have one doubt. This yeah. So here just here, if you take A, B, C are same, so is there any meaning here?
So if
Like
A
is, yeah,
is
means
A is equal to B isn't equal to C, you mean?
yeah, you're right.
Then you get the idempotent axiom. So this implies that if I take A, right, that's the same as A.
Okay, yeah. Oh, very nice. Thanks.
Okay.
That's
yes.
why. Okay. Go ahead, please. No.
Okay. Thank you. Thank you for your question. And again, please, if you feel unsure about anything that I say or write, just ask the question. Okay, the second example, and this is related to group theory and the motivating example for preference and Baer is, so if I take G a group, then G is a heap with operation A, B, C is equal to A, B inverse, the inverse operation in the group, C. Okay, and that's this example, and you can easily check where the multiple identities are very easy to check, because when A is equal to B, then we will get C, right, the cancellation.
So that means a group together with this operation is a heap.
That's right. Yes.
Okay. Interesting.
Yeah. So every group is can be made in the heap if you replace the group operations by the Stirner operation.
Okay.
But of course, not every heap is a group, because the empty set is a heap, but the empty set is not a group. So there is one example which is not a group. And the associativity just follows from the associativity of the group operation. So it's easy to check. And also this example shows what happens with the middle element here in the terminal operation plays a different roles. So if I tried to, so this suggests that if I do this A, B, C, D, E, if I shift this by 1, the middle bracket by 1, then we will have A. And then because we have the inverse here, it means that we applying inverse reverses the operation, we will have D, B, C, E. Okay, so note that there is a change of D is sitting on the 4th place here and on the 2nd on the right-hand side. And so that's something that this example suggests, and actually this is true. You can deduce from the axioms of the heap that the third possible placing of the inside bracket involves changing the order of elements. And if G is abelian, then as a group, then it is abelian as a heap. Because then if it's abelian, then I can swap first with the third elements, and so ABC will be equal CBA. And of course, again, the middle term plays a special role. So for I would like to make a distinction between a group and a heap. So for when I take a group and understand it as a heap, a group G understood as a heap is denoted by H of G. And the reason for this is, first of all, not every heap is a group. That's one reason, but perhaps the more important reason is that if you look at the categorical side of this, not every group homomorphism is not every heap homomorphism is a group homomorphism. Because from the axioms of a group homomorphism, we immediately deduce that a group homomorphism has to preserve the neutral elements, send a neutral element of one group into a neutral element of the other group, while a heap homomorphism has no preservation property whatsoever. So once you convert a group into a heap, and then you think about the homomorphism, then you have more homomorphism in heaps than in the corresponding group. Okay, but in fact, there are more, well, in the classical group theory, there are a lot of heaps, which until the heaps were introduced, we didn't realize they were heaps. So let me, I said something very mysterious, but it's very simple. So let H be a subgroup of a group G. Then for all elements A in G, the coset AH, okay, so all elements H in the subgroup H is a heap with the same operation as the heap operation on a group. So if I take X, Y, Z, then, sorry, this should be X, Y inverse Z. And this was shown by Jeremiah Certain, I think in the 94th. That in fact, there are a lot of heaps in every group. Inside every group, there are, and the group itself can be seen as a heap, but inside the group, there are a lot of heaps, subheaps of the group structure. And so let me just do a quick check of this. So if I take X, so check H1. Okay, so all elements of AH have this form. It's an A and something in H. Y AH2, Z AH3. Then X, Y inverse Z, it's AH1, AH2 inverse, AH3. Okay, so it's AH1, H2 inverse, A inverse AH3. These two terms cancel each other out. So we have A, H1, H2 inverse H3. And since H is a subgroup of G, this element is in H. Okay, so the whole thing is in AH. So this operation is closed under the, well, it's inside, it's an operation on AH under a given coset. And checking the axioms is just exactly the same as in the group operation and heap operation related to a group. Okay, so these are three examples of algebraic nature. So the next one is a bit more geometric nature. And that's the one that I'm very interested in at the moment. And also explains statement that, or some claim that heaps are affine versions of groups. So the next example comes from the theory of affine space. So let me just remind you. So if we have a, okay, so we take K a field. And an affine space A modeled on a vector space, and I will write it as A bar, is a set with a free and transitive action of the additive group of the vector space A arrow. Okay, so to be, it might sound a bit mysterious. So what it actually means is that for all elements A in A and all vectors V in A, the vector space, there is unique A plus V in A, not in the vector space, but in A, such that A plus, if I take two vectors, add them together and add it to A, then it's A plus V plus W. A plus zero vector is A. And the second condition is that for all AB in A, there exists a unique vector, which is usually denoted AB vector, such that the point B is equal to A plus AB. Okay, so the basic example of an affine space, so if you can think about the plane, okay, the usual plane, and if you take any line, not necessarily going through the origin, then you can draw a line parallel right? Going through the origin, this is a vector space. So this is A. This is now a vector space, a arrow. And if I take a point here, then and a vector, say V, right, here, then I can move A by the vector V to point B. Okay, and whenever I have 2 points, A and B, then I can find a unique vector which moves me from A to B. So that's a concept of the affine space. And A is a heap with operation. It's actually an abelian heap. Maybe I should write an abelian heap with operation ABC is equal A plus vector between B and C. So if you have 3 points on the line, then what you do, the operation ABC will be take a vector between B and C, okay, and shift A by this vector. Now, this is not at all surprising because every affine space can be seen as a subgroup, at least as a subgroup of the, or can be sensed or seen as not as a subgroup, as a, sorry. So every affine space, just like in this example, can be embedded into a higher vector space, higher dimensional vector space by adding one more dimension. And then this affine space is exactly a coset, one of the cosets of the additive group. And by the previous example, a coset is always a heap. Okay, so I will not go through the proof here, but it's that's the motivation why this is true, that you can shift it and you can define the heap structure on an abelian on an affine space. Now, an interesting point about this is that when we study, so it's going into affine, the theory of affine spaces, when we normally define an affine homomorphism, then maybe I will come back to this later in a bit more detail. But when we the homomorphism of affine spaces is usually a pair, so it's a function between the sets A and say B. And it has a companion linear transformation from the corresponding vector spaces, A arrow to B arrow, such that when we apply this linear transformation to a vector between points and B, this is the same as F, affine transformation applied to points separately and then taking the vector in between the resulting points. However, when we formulate the affine spaces using Turner operation, using just the heap operation, then we don't need to mention vector spaces at all. We just get the homomorphisms or affine transformations are just heap homomorphisms. Okay, so these are the examples. Let's see, 3 examples. So now it will be 4. And one of the examples, the second one that I gave, was corresponding to groups. So let's look at the relationship between heaps and groups. So heaps versus groups.
Professor, sorry, there is a
Yes.
question in the chat box.
Okay, thank you.
Mhm. Maybe on the first example or the second example.
Okay, so yes, that's probably I made a mistake.
Oh.
Let's have a look. What did I write? Yeah, you are right. Thank you. So sorry about it.
Oh, yeah.
This should be, so C is fixed. Oops. So it's DCB. Thank you very much for pointing this out. Thank you. And thank you very much for paying attention to what I write. Okay, so so heaps, the relation between heaps and groups. So we know that for every group we can assign a heap. So I can state a theorem of two parts: the assignment G to H of G and group homomorphism just to itself is a functor from category of groups, which I write GRP, to, let's write this, H heap, the category of heaps. Okay, so in case you are not familiar with the categorical language, then what it means that, as I explained in the example, every group can be seen as a heap, and then every group homomorphism is automatically a heap homomorphism. That's what it means. Now, in the opposite direction, so if I start with a heap, for any heap H and element E of H, the set H with the binary operation A, I will write dot E, B, a good idea. Okay, maybe I write plus E, B, defined as A, E, B. Okay, so we have a fixed term in the middle, that's E, and this reduces the ternary operation to a binary operation. Is a group abelian if H is abelian. Known as a retract of H at E, and I will write for this GHE. Okay, so what I'm claiming is that we have a group structure if we restrict to the binary operation, and this is for every element of heap. Now, what happens with group homomorphisms? For heap homomorphisms, if f h to h prime is a homomorphism of heaps, then for all E in H, E prime in H prime, I can define two group homomorphisms between corresponding retracts. So if I can write, let's write it like this: E prime E, E, E prime. So this will be maps from H to H prime. F E, E prime of A is equal to bracket F of A, F of E, E prime. And F of E prime E, the other way around, of A is E prime, F of E, F of A, are group homomorphisms. From G, the retract of H, to the retract of H prime. Okay, so we don't have a group homomorphism automatically from the heap homomorphism. We need to make a correction. And there are two possible ways. Of course, if in the abelian situation, they are both the same, because I can swap. In the abelian case, I can swap this term with that one. So these two maps are coincide. Now, the next observation is that what happens, okay, so yeah, the next observation is what happens if I take different, now let's think about this. So now we have a method. Starting from a group, I can produce a heap and I can go back to a group by selecting an element. Or I can start with a heap, produce a group, and go back to the heap. So for all heaps H and elements E of H, we have the following, that if I start with the heap, I produce a retract, and now I have a group. Out of this, I can produce a heap, and what I get as a result is my original heap. And for all groups, G and elements X in G, okay, I can, when I start with a group, I can produce a heap out of it. So now I have a heap. I can select an element, it's called X, and produce a group by taking a retract at this element. So we generally don't get the original group, but a group isomorphic to the original one. So let me just prove this theorem, or just give some hints how to prove it. So part one is just the same as example 2. Okay, so there is nothing to prove. For 2, right, so the statement 2 here was, let's go back, is that if I select any element and out of ternary operation create this binary one, then this will be a group operation. So I need to specify what is a neutral element. So E is a neutral element. For the operation plus E, since if I take E plus E A or B, it's E, E, B, but then the Maltsev identity tells me that this is B. So indeed, E plus B is B, and A plus E, E is A, E, E. Then again, by Maltsev, we get A. So that's a neutral element. The inverse of A, so I will write minus E A, is given by E A E. So just check that this is true. So if I take A minus E A, okay, so by definition, this is how should I understand it? Okay, I should understand it as we normally don't say this that way, but that's what it actually means when you write minus, is we write A plus the inverse element, right? That's what is the meaning of this. Okay, so I know what plus E is. It's A E minus E A. So that's A E, and then we have E A E. But then I have associativity, so I can rewrite it as A E E A E. And now I have Maltsev identity. There are two E's sitting next to each other, so this reduces to A E. And again, Maltsev to get just E. So indeed, this minus E is the right inverse of E, and similarly, plus E A is equal to E. Okay, so indeed we have a group structure here. For the third statement, it was about homomorphisms. So let's look at, say, the first one. I will show that the first one preserves the group operations. So if I take F E E prime of A plus E B, okay, so remember what I want to show is that this is the same as F E E prime of A plus E prime F E E prime of B. Okay, so with using definitions, so the definition for F of E was F of A plus B, so that's A E B. Then we have F of E E prime. Now F is homomorphism of heaps. So F of the bracket is the bracket of the values. Okay, then I can shift this bracket to the right, this internal bracket. So this associativity tells me this is the same as of f of A, f of E. And then here I will have f of B, f of E, f of E prime. But the expression here is just f of A, f of E, and then I have f of E, E prime of B. So that's the definition of the map f, E, E prime evaluated B. So that's the f of B with correction. Sorry, I did it. There is no f here, right? There was no f in the above, just E prime. Okay, but then what I can do, I can use the Maltsev identity, f of A, f of E, and then insert here E prime, f of E, E prime B. Then associative law will tells me that this is the same as f of A, f of E, E prime, f E, E prime B. And now if I look at this bracket, this is definition of f of E, E prime of A, E prime, f E, E prime B. And the last observation is that's the definition of the plus E prime. This triple square bracket is the definition of f of plus E prime. So it's f E, E prime of A plus E prime, f of E, E prime B. And that's exactly what we wanted to prove. Okay, wanted to prove the equality of this with that, the group homomorphism property. A similar proof for the other identity. Okay, so the fourth statement was that if I take a heap, convert it into a group, and then convert it into a heap again, then I will get the original heap. Okay, so I have a heap H with the bracket. And then select an E in H. And calculate the heap on the corresponding group. So that I will write it like this, A, B, C. It's a heap operation, but related to the group H, G, H, E. So what does it mean? That was A plus, okay, that's the group operation E, the inverse of the middle term, plus E, C. Okay, so it was, remember it was A, B inverse C, the group operation, sorry, the heap operation on the group, A, B inverse C. So now the group operation is plus, the inverse is minus, so that's what it is. Okay, using associative law, I can write it like that. It has to deal with the square brackets, which I will do next. So if I rewrite use the definition of plus E, that's AE. Okay, and then we have minus EB, EC. AE, and then minus E is EBE, EC. Right, so now what I can do is I can shift the inside bracket in this expression of 5 entries. So there's associative law, E, E, B, E, C, right? Then the Maltsev will tell me that I can reduce those E, so Maltsev. Tell me that I've got this, then we have associativity. Again, now it's A, E, E, B, C. And then Maltsev. A, B, C. Okay, so the heap operation that we get here from the defined group operation is exactly the same as the heap operation we started with. And for the last statement, when we have this isomorphism, so G to G of H of G retracted at X is simply given by an element of group goes to A of X, no inverse, just X. Okay, so you can check that this is the isomorphism. The inverse of this is obviously you replace X by X inverse, multiply from the right with X inverse. Okay, so what one should remember is that every group produces a heap. Every heap produces as many groups as there are elements of the heap. But these are not different groups. I mean, they're different, but they are all isomorphic to each other. And every group homomorphism is a corresponding heap homomorphism. Every heap homomorphism has to be corrected to be a group homomorphism. And the operation when we start with a heap, turn it into group and go back to the heap, produces the same heap. Which is the last that I said is very useful because we are from elementary school, really, when we started to do arithmetic of numbers, we are dealing with binary operations. Addition is always a binary operation, and subtraction, multiplication, we always think about it as a binary operation. And so we have this tendency, and if we have more than 2 terms, then we split it into pairs. So we are very much used to do binary operations, such as group operations, but not so used to do ternary operations. But this last observation that heap turned into group and then back into a heap is the same heap tells you that if you want to do some algebraic calculations in heaps, you can always convert it into a group, do a group operation, and then revert it to a heap at the end. And in those manipulations, you haven't lost any information. Right, so let me just finish the first part of this lecture because I have something like 18 minutes, I guess, before the break. So some properties of heaps. This will be item number 5. and I will write it as a theorem. In a heap H and any elements A, B, C, D, E, all in heap. I will just rewrite now, stated formally, the missing associativity. So if I move by one, then I will have A. Now I should write it correctly. D, C, B, the three middle terms backwards, E. In the equation, A, B, C equals D, any three elements determine the fourth one. So what I mean by this, that if we have equation in which A, B, and D, say, are known, then I can calculate what C is. I can find an expression for C in terms of A, B, and D. And if I know A, C, say, and D, then I will be able to find what B is, how to write the expression for B in terms of A, C, and D, and so on. So whatever combination of three we treat as known, then the fourth one can be derived. A is equal to B if and only if A, B, C is equal to C. And this is for all C in H. Okay, which tells you that somehow if you go from the equality to the other side, then it's much more work to do. I mean, to compare two elements, well, you just have two elements in here, and here you have to run through all the elements of the heap and check whether this equality A, B, C is equal C holds for all elements C. So it looks like we are multiplying our work. However, so I can say that if H is not an empty heap, then this is also equivalent to A, B, C equal to C. There exists C, so I should write exists C really at the beginning. There exists C such that A, B, C is equal to C. So it's enough to find one if we are dealing with a non-empty heap. Well, in an empty heap, the equality of two elements doesn't really make sense because there are no elements. So the whole statement makes sense only if we have a non-empty heap, but to be precise completely. So if we find just one C for which this equality holds, then we know that A must be equal to B. And this is a very useful property. It helps a lot in solving the problems of solving the equations, equality of sides of the equation. And last property that I wanted to mention is that in an abelian heap, okay, if I consider, I don't know how to state it. Okay, so let's write expression like this, and I will explain it in a second. X1, Y1, X2, Y2, and then I will have yn xn plus 1. So what I mean by this expression is that I put brackets here in the in any order I want. Okay, so I should think about it as triples, but I write them in any order I want. So what I should, and that's in an abelian heap, then this is always the same as x sigma of 1 y psi of 1 and so on, I psi of n x of sigma n plus 1, where psi sigma where psi is in the symmetric group of elements 1 n plus 1, and psi is an, so in other words, permutation 1 to n. So in other words, what I mean is, in the abelian case, wherever we place the brackets, we can always reshuffle elements which are sitting in the even positions with the elements which are sitting in even positions, or those in the odd positions in the bracket with those in the odd positions. And the proof for all these statements, just pick up your favorite element in the, convert heap into a group with respect to any elements of the heap, and then check that properties hold in groups, and they just hold automatically in groups in many cases. This is just, 3 is just, 2 and 3 are just cancellation laws in groups. And if it's true for one of those chosen retracts, it will always be true for all of them, because of the property that if you convert a heap into a group and then back to a heap, then you always get the same heap. Okay, so one more thing perhaps that I should mention. So let me just, my notes. Okay, so we have a so this property 4 yields reshuffling and cancellation rules for abelian heaps. Okay, so what I mean by this is that whenever we have an expression x1, x2, x3, x2n plus 1 in an abelian heap, and whenever we have an expression like this, then it doesn't matter in which way we place the brackets. So I'm not writing the brackets because I could place them starting from the left side and building from the left, or from the right, or from the middle. It doesn't really matter in the case of an abelian heap. And I can label those terms plus and minus to indicate which are sitting on the odd even positions. And plus and minus because if I think about this inside a group, and that this will be an abelian group, this expression, so in an abelian group, it will look like this: x1 minus x2 plus x3 plus x2n plus 1. If I convert it into using the group operation, into a group operation. So whenever we have an expression like this, we can always, and we spot that, say, x 1 is equal to x2, then the Maltsev identity will allow us to cancel them out. If x2 is equal to xn plus 1 as well, because I can reshuffle the elements inside the bracket in the free way, and keeping pluses and minuses labeled as pluses and minuses in the right position. So pluses in odd positions, 1, 3, 5, and so on, minuses in the even ones, and then cancel the terms which are the same on the but with the opposite signs. Okay, so one more thing before the break and possible questions. Subheaps. So whenever we have an algebraic structure, we would like to have a substructure. So subheaps. Subheap of a heap H is a subset closed under the heap operation, which means that x, y, z for all x is a subset S. X, y, z in S. Whenever I take this combination x, y, z, then the outcome is in S. Any subheap S defines an equivalence relation in the following way. So A is in relation to B, so A, B are in H. If and only if A, B, S is in S for all elements S of the subset, or equivalently, maybe I should say any non-empty subset S defines an equivalence relation, or equivalently exists S in S such that A, B, S is in S. Now, how do we see that this is an equivalence relation? Since A is always in relation with itself by Maltsev, since whatever S I take, A, S is equal to S, so it's an element of S. Now, if I look at symmetry, so that's a reflexivity, reflexive, symmetric. Okay, so suppose that A is in relation with B. So I know that I have T, an element of S, such that I have A, B, S. Then if I look at B, A, T, that's BA, ABS. So the associative law will tell me BA, ABS. Multiple identity will allow me to cancel A's. So we have B, B, S, that's S. Again, by the multiple, so we are in S. So I take an element of S, I find out by definition that AB, this element is an element of S again. So I have an element of ST, and I calculate BAT and find that the result is in S. Hence, B is in relation S with A. So the operation is symmetric. So reflexive, symmetric, transitive. So if I take ABS is equal some S prime, C okay, so what I assume is that A is SB, B is in relation S with C, which we already know that's the same as C is in relation S with B. So I can take C, B, and S again, and this will be another element of S. And then ACS double prime, that's AC, CBS. Associativity will tell me that's ACC, BS. It's ABS, but ABS is S prime. That's an element of S. Hence, A is in relation S with C. Okay, and so we have an equivalence relation related to a subheap, just as, and I've written this entirely in terms of heaps, but again, you can refer to the group, to the group retract of the heap. So you can, if you select a retract of H at any element of S, then the condition of a subheap corresponds to the condition of a subgroup, and the relation, equivalence relation, is just a subgroup relation. Okay, so I think I will stop now. Any questions?
Okay, okay, thank you so much, Professor, for the great and detailed lectures. So that was the first session of today's lecture. And I believe that some of you have questions to be asked. So I will open the short Q&A session before the break. So yeah, you can ask from the chat, or you can directly turn on your microphone. Oh, this one from City.
I will have a look.
Yeah, Professor, for number two.
Group. How about if we take a different E? Does the resulting group is the same? Okay, so there are quite a few questions. So the first thing is so the answer is okay. Let's go back. I will read it out just for everyone to. Properties from heap to group. So the question is, what is the relation between GHE and say GH some other E prime? So the question is, are they equal, or are they or what are they? So the answer is, they are not necessarily equal, but they are isomorphic. And one way of, you can directly write down the isomorphism, but one way of seeing this is also going through 5, because for all groups G and H, I can take X and G. Okay, well, how do I want to play it? Yeah, I can start with the, okay, I really should start with H. Yeah. You can combine the isomorphism here. It's the same G in the middle, and you combine the isomorphism for different X and say X prime. But you can also write down the isomorphism explicitly. So let me think what it would be. To make it so isomorphism here between the groups, I think it is F of A is A E E prime. It's a so-called translation isomorphism. So they are related by translation. So if you can see that F of E here will give E prime, which is okay. And you can check that this preserves the group operations as well. And the inverse of this, F inverse of A, is A E prime E. So F goes from GHE to GHE prime. So in general, you don't get the same group, but all the groups are isomorphic. So the second question, also in the groups, we know about the kernel of homomorphisms. How about in heap, since we don't have the identity element? Okay, so we can define a kernel. So I didn't get to this, and I was not planning to mention this, but since you asked about that, we can define something which is called a relative kernel. So if I take a homomorphism of heaps, H to H prime, and select any, say, E prime in the image of F, then I can consider the inverse image of E prime. Okay, these are all elements H in H, such that F of H is equal to E prime. And we can call it the relative kernel of F, relative to E prime. And what one can prove is that F inverse of E prime is a subheap of H. F inverse of E prime is isomorphic to F inverse of E double prime. If I take another element, then they're isomorphic as heaps. What one can also prove, that's the next property, is that, so I haven't mentioned this, but just like in the case of groups, we have subgroups and normal subgroups. We have heaps and normal subheaps. The difference, as you know from the group theory, is that if you take the subgroup, if you take a quotient by a subgroup, you not necessarily get a group. To get a group, you need to take a quotient by a normal subgroup, get a group structure. Otherwise, you get a just the set of cosets is a homogeneous space, but not a group. So similarly in the heaps, if you take a normal subheap, then you will get the quotients relation, the set on the set of quotients of equivalence classes, you will get a heap structure. Okay, so what one can prove is that this is not a subheap, but not only subheap, but it's a normal subheap. So since it is a subheap, we have the relation, subheap relation, just as I explained a few minutes ago. And this relation, so the relation is the same as E prime, E double prime. So if I take the different elements, I get the same relation. In other words, the quotient set that we get this way, whichever one we take, whichever one we take is the same. The set of quotients, or the set of equivalence classes. And this goes to the concept in the universal algebra, where we don't talk in the universal algebra, we don't really talk about kernels, but about kernel relation. So a kernel relation, is defined as follows. Very simple relation. So if we have f from h to h prime, a homomorphism algebraic structures, for example, heaps, groups, rings, and so on. So if we have such a homomorphism, then we say that X is in the kernel relation F with Y, so that's a relation, if f of X is equal to f of Y. So in case of groups, okay, so if H and H prime are groups, then the kernel F is the quotient relation by the kernel, well, the group kernel of F. Okay, I'm using the same, maybe I should underline it. So that's the usual kernel of the group homomorphism. Groups, rings. The kernel is just the quotient relation by the kernel. And also from the universal algebra, we know that the quotient set H by the kernel relation is an algebraic structure of the same type as H. So in the case of groups, the kernel of a group homomorphism is a normal subgroup, and the quotient is a group. In the case of rings, the kernel of a ring homomorphism is an ideal, and the quotient of a ring by the ideal is a ring again, and so on and so forth. And in the case of heaps, this kernel relation corresponds exactly to those the relation, the subheap relation by the by those relative kernels. Okay, so it's a short question but long answer.
Yeah.
But it's I think it's one of the very nice things about heaps, that once we start, or ternary operations, that once we start dealing with formulation of groups in terms of those ternary operation, we no longer need to fixate on a particular element. Every element can play exactly the same role. You see, in the group, we have one particular element which has a special role. That's the neutral element, the zero of the abelian group. It's a very special element. And from the distributive law, the ring distributive law, as I explained at the beginning, or recalled at the beginning, you can't invert it with respect to multiplication. You can't divide by zero. In principle, you can divide by any other element in the ring, if you do localization, or but not by this one. You can't do anything. You can never divide by zero. So it's a very special element. And somehow this existence of a special element dictates us that we should use this. So we define the kernel for groups by the inverse image of the neutral element. The kernel for rings, again, is an inverse image of the neutral element of the additive group, and so on and so forth. But in fact, we don't have to, we can use for this purpose to define the kernel any element of a ring, any element of a group. Sorry, but we have to think about it more in terms of what actually kernels do. So they provide the relation and the quotient process rather than what they actually are.
Okay, thank you so much, Professor. Yeah, yeah, I think the time is up for the Q&A session. Maybe if you have any other questions, we can proceed it on the next Q&A. So thank you so much for Professor Brzezinski, and also for participants. However, we have to have a break first for 30 minutes. So Professor, as well as all the participants, you might take a break for 30 minutes. So see you in the next.
See you in half an hour then.
Yeah. Okay, thank you so much.
Yes, please ask the question.
Yeah. Okay, so we have 5 minutes left, but yeah, maybe we can try to see what's the next
I can
question.
see that someone wants to ask a question about, yeah. So
maybe she's writing now.
So if I may ask a question, so the second part will also be 90 minutes, right?
Yeah.
Last question.
90 minutes. Yeah. Okay, so maybe she is still writing.
I will be back in a second.
Yeah. Okay, participants, we will get back to the next session. So yeah, please get back to your seat and be ready. Okay, while waiting for the question, maybe we can start again. So good afternoon, everyone. So how's your break? I hope it can refresh your mind and makes you ready for the next session. So yeah, perhaps. Wait. Oh, that's. Yeah, there is a question from Nia. Before trusses notion introduced by you, does heap has a specific application in physics or anything? I mean the motivation of this notion, because like you said before that we used to the binary operation and it is a bit difficult to work with ternary. Is it just because we want to have a group-like structure without identity element? Heap was introduced long time ago, but I just know the notion today. Okay, maybe.
Okay, so frankly speaking, I don't think that heaps had real application in the whether in physics or in mathematics. They just appeared at different stages. So the first in the 1920s, and then they just appeared and disappeared. And I don't think they had any particular application. Then in the 1960s, in the work of in algebraic geometry, where torsors are, so it was realized that the structure of a homogeneous, not a homogeneous space, but also in more general, a principal bundle, a bundle with where the fiber is a group, has the structure of a torso. So the Stirner operation can be converted into the Stirner operation. It's a group acting on a space in the free and transitive way. So this appeared, and I don't think, as far as I know, and there's very limited, the literature on heaps is very limited. So probably they didn't have any specific application.
Okay. So yeah, for the next question, is it just because we want to have a group-like structure without identity element? Is it right, Professor?
Well, it's a concept. I think I mentioned this, that it's a sort of affinization. So it's a fine version of a group, where indeed we don't have to have any fixed element, and not only the identity element, but any fixed element. So now that there's one other area where, well, I don't think people really looked at heaps, but they looked at affine spaces. So there was a program in physics developed mainly by Turcheyev and his collaborators, his students, and also some group in Italy. I don't remember the names of the physicists, where the idea is that to develop mechanics without an observer. So in physics, there is a role of observer, someone who observes the phenomena, physical phenomena. And so this is a point in the space which plays a particular role. And normally it would be chosen to be the identity element or the zero of the vector space, the zero vector in the vector space, the origin of the space. But there was this program of looking at mechanics without an observer, without specifying the point. And then it leads to affine spaces, and the natural way to go from there is to view affine spaces as heaps. And I will explain it a bit more and then trusses. I will explain it a bit more in this part of the lecture, I hope.
Okay, thank you so much.
And also, so another area in physics, maybe it's been earlier than mechanics, it was in quantum field theory, in gauge theory. Alan Weinstein, a mathematical physicist from Berkeley, he was doing or suggesting to develop a so-called gauge theory without fixed gauge. I don't want to enter into this physical explanation, but a gauge theory is a theory which really explains interactions of physical interactions in elementary level.
Okay. Okay, thank you so much, Professor. Maybe is there any question again before we start? Actually, I have a question. May I?
Yes, please.
Yeah, yeah. Maybe it is about it's a bit to make sure about my knowledge. I want to make sure about the homomorphism of heap. You said that all group homomorphism is a heap homomorphism, right?
Yes.
Then how about the three isomorphisms theorems that work in groups, ring, and so on? Is it also work fine in heap too? Or
yes,
is there any differences?
I don't know. The difference is, so the first isomorphism theorem involves the notion of a kernel, the image and the kernel. So the image of, but those theorems are actually true in many algebraic systems. So it's wherever they are, and they hold in universal algebra, and it's also in the case of heaps.
Okay, thank you so much, Professor. Yeah, maybe because there is no other question, we can continue to the second session. So, Professor, you might start the session now.
Okay, so I will start with well, now trusses. That's the topic of the seminar, in a way. So so let's start with the definition, and then I will try to give examples and some properties and some motivation. I'll go back to motivation. So first of all, what I try to convince you in the first part is that we can look at groups in terms of Turner operation as heaps. Therefore, if we think about a ring, we can replace the addition in the ring or addition in the braces that we described briefly at the beginning of my lecture by the corresponding Turner operation. And then we will have a system consisting of Turner operation and binary operation for multiplication and some interaction between them. And the natural way is the distributivity. And that's exactly what a truss is. So let's start with definition. Okay, so I left, right or right skew truss as a heap T, okay, and then we have a Turner operation. With an associative binary operation, say dot, such that which distributes over the Turner operation. So in the case of left, it will distribute from the left. So A dot B C D. It's just bracket of A dot B, A dot C, A dot D. I will write in the brackets the distributivity for the right heap, so right truss, skew truss. So A B C dot D is A dot D, A dot B, B, B dot D, C dot D. Okay, so that's the definition. So I left skew truss is a heap with an associative binary operation, which distributes over the heap operation from the left. A right skewed truss is the distributivity from the right. Now, if heap is abelian, we drop adjective skew. Okay, so when I say a truss, a left truss will be an abelian heap with the multiplication which distributes from the left. And left and right truss is simply called a truss. Okay. Rather than saying a two-sided truss, I would just say a truss, and it means that. So, what are the properties or the defining properties of a truss? It's an abelian heap. So this now operation, the heap operation is abelian, and we have two distributive laws, the left one and the right one. Just like in the ring, we have an abelian group and two distributive laws, from the left and from the right. Okay, so that's the definition of a truss. So let me start by giving you some elementary examples. Okay, so the first example which I really like is the example of coming from arithmetic of numbers, like whole numbers. The set of odd integers, 2z plus 1, is a truss with now Turner operation. A, B, C is equal to A minus B plus C. Okay, so the first thing that I need to say is that, well, this is indeed a heap operation because, well, 2z plus 1, first of all, it's a coset of the, if we take a subgroup of even, that's right? Yes, so the subgroup of even integers, then the coset corresponding to 1 is the set of odd integers. So by general example of heaps, as cosets being heaps, this is a heap. But also more elementary, whenever we take the operation of 3 odd numbers, then we will get, if A, B, and C are odd, A minus B is even. Adding to this an odd number gives an odd number. So this is a well-defined operation on the odd integers are closed under this operation, and it's obviously commutative, so it will be a Abelian operation, and it satisfies the heap definition. And the multiplication is the usual multiplication of odd integers. And an important thing here is that if you multiply two odd numbers, you get an odd number. So this is well defined. And the distributivity is sort of obvious because we have the distributivity of multiplication over addition, and the Turner operation is built from addition. So obviously the distributive law will carry over to the Turner operation. Okay, so So this is a nice example. I mentioned why that I like it very much, because you see, if I think about subrings, and the ring of integers itself is a truss. And if I think about subrings, then odd numbers are not a subring, because the subset is not closed under addition. If you take two odd numbers, add one to the other, you'll get an even number. So it's not closed under addition. But if you think about integers as a truss, and that's probably one of the examples I should mention from the very beginning. So if you think about integers as a truss, then both even and odd integers are subtrusses. Okay, so let me just give you a general example. If R is a ring, then R is a truss with respect to, okay, the heap operation is the heap built on the additive subgroup. So RST is R minus S plus T. And the original product. Okay, and when thinking about the trusses, or maybe I should go back to the definition. Sorry for this jumping, but I've forgotten to say that homomorphism of trusses is a homomorphism of heaps that preserves multiplications. Okay, so it's a homomorphism of both heaps, I explained what it means, and semigroups, so it preserves the multiplication. Okay, so if R is a ring, then R is a truss with respect to this heap operation and unchanged product. And so I can think about a ring as a truss when thinking about R as a truss, we will write T of R. So truss built on the ring R. And this T is a functor from the category of rings to the category of trusses, because every ring homomorphism will be a truss homomorphism, because every ring homomorphism is a homomorphism of abelian groups, hence the corresponding heaps, and preserving multiplication. So that's the second requirement for the truss homomorphism. Okay, the third example comes from the again from arithmetic of numbers, this time of fractions. So the set of odd fractions 2z plus 1, so odd number in the numerator and odd number in the denominator, is a heap with the heap operation. So now we can write PQ, P prime, Q prime, P double prime, Q double prime. The same operation as before. So it's just difference. So it's plus difference q prime plus q double, so p double prime by q double prime. Okay, and I can pause here for a second because I need to know whether the operation is well defined. So that's the definition, but I can put everything on the common denominator. Q prime, q double prime. Then this will be p q prime, q double prime minus p prime q double prime plus p double prime q prime. So remember p prime, p double prime, and p q prime, q double prime, they're all odd integers. Right, so in the denominator, I have the product of 3 odd integers. So this is an odd integer, so that's fine. And in the numerator, I have odd integer minus odd integer plus odd integer, which is an odd integer. So that's indeed is where it should be, z plus 1 to z plus 1. And the usual multiplication. Of numbers, because we multiply numerators, so to odd numbers, we give odd number, and denominators, to odd numbers, we give an odd number. Okay, so this example is interesting because note that 1 is an element of 2z plus 1 by 2z plus 1. Okay, for example, I can write 1 as 3 by 3. So it's a fraction of 2 odd integers. And PQ inverse is Q over P, and that's for all PQ in this set. So there are no restrictions. So 2z plus 1, 2z plus 1 with multiplication is a group. Okay, so we have this particular truss is a system which is on the same set. We have 2 group operations. One is the addition. Sorry, I put it wrongly. So now it's a heap operation. Okay, it's a heap operation, and multiplication is a group operation. Okay, but we can consider the group, the retract of the heap at 1. This will be a group. In other words, I wrote plus and 1 in the decoration here to be consistent with the other notation. I have a group operation defined like this: PQ1, P prime, Q prime. Okay, so it's PQ minus 1 plus P prime, Q prime. So I can write it more explicitly, QQ prime. And then I will have, what do I have? I can write this as PQ prime minus QQ prime plus P prime Q. Okay, so I have this binary operation. You can easily convince yourself that it has an identity. It's a group operation. With identity 1. So on the same set, we have two group operations which interact with each other. So in other words, this is an example of a brace. I will, so to be precise, when I start with this truss and then take a retract of the heap at identity of the multiplication, I will get a brace. So this already indicates that in the same umbrella, and the same umbrella of trusses, we can have examples of rings and examples of braces. Now the next example is very general one, and this goes back to the standard fact in the ring theory, that if you have an abelian group and you look at the set of all homomorphisms from this group to itself, so all endomorphisms of a group, then first of all, they will inherit the addition from the group, but also the composition of functions is then well defined for all elements, and this associative operation and distributes over the addition. We have a ring. And the same is true about trusses, so that we have examples of endomorphous trusses. So let H be an abelian heap. Set E of H to be the set of all maps from H to H. F is a heap homomorphism of heaps. Then E of H is a heap with operation defined pointwise. So what this means is that if I take F, G, H to three functions from H to H and evaluate them, so this has to be a function, and I define this function to be F of A, G of A, H of A. Okay, so now this is a well-defined function, but the question is this a heap homomorphism? Is FGH a heap homomorphism of heaps? Okay, something that needs to be checked. So what does it mean? What we need to check is what happens when I look at the evaluate FGH at A, B, C, the heap operation. Okay, so according to the definition, this should be F of A, B, C, G of A, B, C, H of A, B, C. That's the definition of the bracket on functions. But we know about those functions that each one of them is a homomorphism of heaps. So I can rewrite this as follows. So f applied to the bracket is the bracket of f of a, f of b, f of c. And since we are in the abelian situation, I will not write the brackets inside the brackets because they don't change anything. G of a, g of b, g of c, h of a, h of b, h of c. And now I can look at the parity and oddity of the places, or the parity of the placings. So this, and use the reshuffling rules. So this is odd, even, or the plus, even, plus, even, odd, even, odd, even, odd. And then this expression will be the same, provided, whichever way I reshuffle it, provided I will have the order of plus, minus, plus, minus, plus, minus. So for example, I can keep f of a as the plus position, and then choose whatever I fancy from the negative ones as a next place, because next position is negative. And so let's take g of a here, the negative one. And the next one should be a plus. So I'm looking for pluses, and I like h of a. And the next one should be minus. So I will take f of b from the minuses in this line. And then next one should be plus. So I will take g of b. Next one should be minus. So I will take h of b. And then the last one should be plus, the last triple, f of c minus g of c and plus h of c. Okay, so I rearrange the elements in the expression, but all the pluses are in the plus positions and all the minuses are on the minus positions. So what I've done is completely legal, and now I can just write the brackets for the sake of argument, reinstate the brackets. But the first bracket here is just definition of f, g, h evaluated at a. The second bracket is the definition of f, b, c evaluated, so f, g, c evaluated at b. And the last one is f, so f, g, h. F, g, h evaluated at c. But this means exactly that this function fgh appears 3 times here when evaluated at the bracket of ABC, which means that this is a homomorphism of heaps. FGH is a homomorphism of heaps. Okay, so this operation of pointwise, well, this operation defined by the pointwise operating is a well-defined operation, and it's you can easily check it's a heap operation because, sorry, because on the left-hand side of this definition, by assumption, we have a heap operation. And E of H is a heap. Okay, so now we can introduce multiplication. It's just composition of endomorphisms. Okay, so we know that the composition is an associative operation, so there's no problem with this. The problem is, does it distribute over the heap operation? So we need to check distributivity. So what does it mean? If I take the bracket of three endomorphisms, compose it with the fourth one, I need to check whether this is the same as F composed with K, G composed with K, H composed with K, and then take in the bracket, which means that since they are functions, so I can evaluate them at any element, and then if it's true for all elements, it will be true for functions. So by definition, this is F, G, H, K of A. Okay, so it's F of K of A, G of K of A, H of K of A. So F of K of A, G composed with K of A, H composed with K of A. Okay, so the distributivity on the right holds, but this is true for all functions. I don't even need to consider homomorphisms. So that's distributivity on the right. It's always, if you take a endomorphism or the end of functions on a set, and whatever operation on the set you introduce on the right, it will always be distributive. Now, the problem is the distributivity on the left. So F composed with GHK. Okay, so that's F applied to GHK evaluated A. It's F applied to bracket G of A, H of A, K of A. But now what I can do is I can use the fact that F by assumption is a homomorphism of heaps. So this is the same as F of G of A, F of H of A, H, F of K of A. And that's F composed with G, F composed with H, F composed with K. Each one evaluates that A, so altogether it's this. Okay, so we end up with the equality that F composed with GHK, F composed with G, F composed with H, F composed with K. The distributivity holds. Okay, so that's the. So in this proof, we need to use we are using the fact that we are dealing with homomorphisms. So endomorphisms of an abelian heap form a truss. And in fact, every truss can be included or they're mapped into a truss of endomorphisms of its own heap. So it's a universal example of trusses. Just it's the same true for rings. Every ring can be mapped into an endomorphism ring. Okay, the next example is related to affine spaces. So I explained in the first part that what an affine space is, or recalled, and also that you can define a heap operation on an affine space. So A is an affine space over K. Okay, so it's modeled on a vector space A with an arrow, and we have a heap operation A, B, C is A plus vector from B to C. So now the following is something that we know, that if we have, what is an associative algebra? So an associative algebra over a field K is a vector space, right? A vector space with a bilinear associative operation. It's a vector space, let's call it V, not to confuse with a bilinear associative operation. So bilinearity means in particular that if I take V plus W times U, so in particular for all V, W, U in V, so the multiplication here, so maybe I should write it like this, M V plus W U. So that's multiplication. Well, maybe I should start from the other side. Okay. So the bilinear associative operation M. Okay, so usually we write multiplication by a dot, but this means M V plus W U. But M is a bilinear operation, so in particular it is additive, so that's the same as MVU. It's additive on the first argument plus MWU, which is V dot U plus W dot U. And so that's the additivity part of the linear transformation property on the first argument. And if I apply this to the second argument in multiplication, excuse me. Then we have, so that's M of U V plus W, M of U V plus M of U W, which is U dot V plus U dot W. So we have the, in other words, the inside the property of multiplication, a vector space being bilinear operation, what is hidden is the property that we have a distributive laws, right and left distributive law. Okay, so now the question is, what kind, so suppose we have an affine space A with a bi-affine associative operation M. What kind of distributive laws we get? Now, I need to explain what an affine operation is, or affine transformation, right? Affine associative operation, affine transformation. Okay, so what it is? So first of all, as I recalled, we have the Stirner operation. Because BC is a vector, the vectors can be rescaled. So in fact, we have also another operation corresponding to the scalar multiplication. So I will write it like this. So the scalar multiplication A. So lambda is in the field, and A, B are in the affine space. So what can I do? Well, I can take A and shift it by a rescaled vector AB. So lambda AB. And now, by definition, an affine transformation F from okay, so from A bar to B bar is a pair F arrow, F bar, F arrow. So F maps from A to B, that's a function. F arrow maps vector spaces, so it has to be a linear transformation. Such that, so that's the definition of an affine transformation in the classical sense. So such that for all A, B in A, F vector applied to the vector from A to B is the same as F applied to A, F applied to B, and then the corresponding vector in B, B vector. Okay, so that's a classical definition of an affine transformation as a pair. But what does it actually mean from the point of view of heaps? What is a linear transformation? What is an affine transformation from the point of heaps? Okay, so let's have a look. Let's do a small calculation. So just note, if I look at F applied to the vector BC, okay, so that's what I can do. I can rewrite BC as A plus BC and the vector. And why is that? Because this vector BC is a vector from B to C. If you think about the vector which is here, then what we have is again a vector from B to C. The A disappears because we take a part of a vector which is from A to A. So that's a zero vector. It's just like adding 0 to BC. And we know from definition that if we have 2 points, then there is a unique vector between these 2 points. So if what is written here is a vector between B and C, and here is a vector between B and C. This must be the same vector. Okay, and then I can apply the definition of this property here to write it as f of A plus BC vector. Okay. Okay, so in other words, f of A plus BC, that's the same as a vector. So now if I look at the right-hand side here, so that's a vector between f of A and FA plus BC. And this is also the vector between these 2 points because of the equality. So that's the same as f of A plus f of BC this, but that's the same as f of A, f of B, f of C by the definition of the affine transformation. So now what we derive is the following, that f of what was A plus BC, I will scroll back, A plus vector BC is just the heap operation. So we have the A, B, C here. And here we have again a heap operation, f of A plus f of B, sorry, f of B, f of C. So by just using the definition of using the definition of an affine operation or affine transformation, what we find is that the function f from A to B is a homomorphism of heaps. Okay, and this is important because now assume that multiplication M is by affine. So it's affine on the first and the second argument. Then what we have i.e. for all, say A in A, function B to MA B is affine, and B to MBA is affine. So what we now know is that in particular, they are homomorphisms of heaps. So if I look at the multiplication, say A, B, C, D, that's M applied to A, B, C, D. This is an affine operation, affine transformation, which means that it's a heap operation, as I have just explained. So we have M of AB, M of AC, M of AD, AB, ACAD. And similarly, for the right distributive flow. So what the conclusion is, and a fine space with an associative by affine operation is a truss. Okay, so I think I gave you various examples of trusses. One of them appears to be a brace. Well, we could retract it to a brace. So let's look at a general situation. So this will be 9, I think. 9. So let's B plus dot be a left brace. That is B plus B dot are groups. And for all A, B, C in B, A dot B plus C, A dot B minus, okay, I should say B plus abelian. B plus abelian minus A plus A dot C. Now, okay. How do I put it? Okay, view B plus as a heap, H of B. Okay, so in H of B, I have the operation A, B, C, A minus B plus C. So you see, I have two groups here, so I need to be, each one of them can be seen as a heap. So I select to see as a heap, it's an abelian heap, the one that corresponds to an abelian operation. Okay, so the plus operation. Then HB with a dot, so a heap, and an associative operation is a left truss. Left because I assumed only the left distributivity for the brace. If I assume the right distributivity, I would have a right truss. If I had a two-sided distributivity, then I would have a truss. Conversely, any left truss in which dot is a group, when retracted to G of t at identity of the multiplication is a left brace. Okay, so that's a, let's say, theorem. Let's give it a proof. Okay, so the proof of part one. So first of all, I already mentioned this, but let's show that this is the case. Note that in the brace, or left brace, in a left brace, 0 is equal to 1. So 0 is a neutral element for plus, and 1 is a neutral element for dot. And why is that? Because if I take a dot 0, then I can write it as a dot 0 plus 0, because 0 is a neutral element. By the brace distributivity, that's a dot 0 minus a plus a dot 0. Okay, so we have this equality. So using the cancellation laws, I will have that 0 is equal minus a plus a dot 0. So a is equal a dot 0. Right? But we also know that a is equal a dot 1, because 1 is the identity element for the multiplication. So we have a dot 0 is equal a dot 1. And then, since this is a group operation, so cancellation, by cancellation laws, 0 is equal to 1. Okay, so in the left brace, or and if I don't assume that pluses and abelian operate as a commutative operation, the left skew brace, this is always true, that 0 is equal to 1. Okay, so the next thing to, we have to be careful when we start working with braces, because I write it on the, here in the margin, in a way that we remove it quickly. So from our ring theoretic perspective, we always think that a times minus 1 is minus a, right? Because that's what we immediately get from the distributive laws. But these are distributive laws for rings, so no longer valid in the brace situation. So we have to be a bit more careful here. So let's calculate what minus a actually is. Or what does it mean to multiply a by minus c? Okay, so we know that a is a dot 0. This I have just, because 0 is equal to 1. Okay, so then I can write 0 as c minus c for any element c. But what it is, this is A dot C plus minus C, right? That's what this minus really means. Now I can apply the Brace distributive law and rewrite it as A dot C minus A plus A dot minus C. Okay, so I have the equality that A is equal to this expression. Okay, and then so I can resolve it for A dot minus C. So A dot minus C is equal to A minus A dot C plus A. Okay, putting this expression on the, no, obviously this is not, what did I write? That's right, yes. So if I keep this on the right-hand side and put this expression on the left-hand side, then and then reverse the sides, that's the expression that we will get. And although operation here is commutative, I don't write 2A as we would write A plus A, because if you think about 2 as 1 plus 1, when 1 is identity in the brace, then actually this is 1 is equal to 0, so that's 0. So it's a bit confusing. It's better to write all the terms as they stand, not simplifying them using some arithmetical tricks. Okay, so now I think I have all the information that is needed for proving the distributive law. So what I actually need to prove is that the multiplication distributes over the Turner operation. So we have A dot B, C, D. And then I will be carefully using the definition of the bracket. So it's B plus minus C plus D. Okay, so now I will need to use the distributive laws for the for Brace. So I write all the brackets very carefully. It's A dot B plus minus C minus A plus A dot D. Now we have A dot B minus A plus A dot minus C, a distributive law, Brace distributive law for this bracket, minus A plus A dot D. And now I can use the expression for A minus C, so it's A dot B minus A plus A minus A dot C plus A minus A plus A dot D. So I have A dot B minus A dot T dot C plus A dot D. So that's A dot B, A dot C, A dot D. So indeed, we have a truss distributive law, but on the left, because we are talking about left braces, if I had the right braces, then I would have corresponding right distributive law. Both sides would have two-sided distributive law, so just a truss. So H of B, the dot, is a truss. And the second statement was that if I have a truss in which dot is a group operation. And so the one is the identity for the group operation. When I retract at the identity, I will get a brace. So we note that A plus 1B, that's A1B. And I should also write perhaps minus 1 B. That's 1B1. Note or remember from the first part of the seminar. So it's minus 1B is 1B1. Okay, so now I check the distributivity. A, B plus 1C. So it's A times B1C. We are dealing with a truss, so I have A dot B, A dot 1, A dot C. 1 is the identity, so it's A dot B, A dot C. And then, well, either I can write expression for the minus and write everything explicitly, or to use, well, in the long way, or to use the observation that since we are dealing with a heap, whichever element I will take for the retraction, when I go back to a heap, I will get the original heap. So I would end up with A dot B minus 1 A plus 1 A dot C. Indeed, we have a brace. Okay, so this explains in what way trusses combine braces with rings. The price that we have to pay for this is to view it to move into the heap world and use ternary operations rather than binary ones and to replace the addition by the ternary operation. Now, the next thing that I wanted to say is that, well, actually two things that conclude this seminar really is that, first of all, there are a lot of trusses. So if you start with a ring and look at start with an abelian group. It's a long-standing problem in the ring theory to classify all ring structures on a given abelian group. We have a given abelian group and we ask how many non-isomorphic structures, ring structures you have there. And in the case of, well, you can ask the same question for trusses, or you can classify there is an opposite problem. So suppose that you have a ring, well, on each abelian group, you can define a trivial ring with the multiplication sending all elements to 0. So whatever you multiply, you always get 0. This obviously distributes over addition, and so it's a ring, well, non-unital, but a ring. And then you can ask the question, well, which groups have the property that the only ring structure on them is the trivial one, the 0 ring structure. So they are called nil groups. So you can study which groups have this property. So you can ask similar questions for trusses. So let me just tell you one result about trusses on integers. So trusses on Z or integers, or to be precise, on the heap corresponding to the additive group of integers. So there are actually quite a lot of them. I will not, I mean, how would you go about classifying rings on Z? Well, you know that, well, first of all, multiplication by 0 gives 0. This you know, right? So you already know that multiplication by 0 is 0. Multiplication by 1 is anything, can be anything if it's not a unitary ring. And then you say, well, you then use distributive law. So if you multiply a times n, that's the same as a 1 plus 1 plus 1 and so on, right? Which is the same as a times 1 plus a times 1 plus and so on plus a times 1. Okay, so in the ring situation, if you know what is the value a times 1, 1 is a generator of the group, then you will know the value for the whole for whole group. So all the structures of the ring defined on the abelian group of integers, or infinite group of cyclic group on the group of integers, were just encoded in possible choices of this value, a.1. Well, commutative ones anyway. But in trusses, we have more freedom, because we are not requested that multiplication by 0 will give 0. So this gives you more freedom. And this freedom is such that actually you can find a lot of structures. So first of all, there are non-commutative structures on every abelian group. Maybe this I should say in general. So for any abelian group, there are 3 non-isomorphic truss structures. So one is this, A dot B is A for all AB. This is not a ring structure. You can easily convince yourself that this is, unless you have a trivial ring, one element. There is a corresponding one where you just cut out the first argument. Okay, so 2 projections, and the first or the second argument are truss structures. And there is one A times B equal E, where E a fixed element. It could be a 0, could be any other. I mean, you get you can put 0 here. Maybe I should write 0, because all the others are, you can take any other element, but they are isomorphic. A dot B is equal E, so isomorphic to fixed element. Okay, just like on the question how many truss structures you can construct on a given heap corresponding to an abelian group. So first of all, more than rings, because you have these 2 additional ones which you do not have for rings. But going back to to integers, so we have these 2, the only non-commutative ones, but there are commutative ones. So let I2 of Z be the following interesting set. So these are matrices, 2 by 2 matrices integers with the property that they are idempotent and of trace 1. Trace of P is equal to 1. Okay, then there are the following or maybe I should write just to be before I do this. Let's write those matrices explicitly so that I can use the elements for explicit definition of multiplication. So these are matrices. I will write them like this: BA minus C 1 minus B. Okay, I will write them in this form. So this B 1 minus B is a trace 1 condition. Okay, we have to B plus 1 minus B must be equal to 1. So, and the condition on the remaining ones coming from the idempotent property is that AC is equal to B minus 1. No ABC in Z. So we have truss structures on Z. The non-commutative ones, which I already mentioned, Mn is equal to N. This is, of course, for all Mn in Z. And the commutative ones have the following property or product, M dot N, that's the product in the truss, A times N times N. Let's write this dot here. So this is multiplication in integers plus B times M plus N plus C. Okay, so there's quite a number of them. And so these are truss structures on Z. Now I'm not talking about interrelation between them. So obviously this one is not isomorphic to that one and neither to this one, because the first two are non-commutative and the last one commutes, the operation commutes, multiplication commutes. So I will write for this one ZABC. And ZABC is isomorphic as a truss. So some different choice of parameters. If and only if B tilde, A tilde, minus C tilde, 1 minus B tilde is equal to 1, 0, K plus minus 1, BA minus C 1 minus B, 1, 0, K plus minus 1 inverse. For some K in Z. So the elements here are elements of the infinite dihedral group. And then the number of the number of possible possible non-isomorphic structures depends on the nature of those parameters A, B, C. So, for example, if A is a power of the prime number, then there are no idempotents. So they're different from no idempotent. So then we don't have any structures. If the A is a power of the prime number, then we don't have any structures. Okay, so that's just a taster of what one can do with the classification problem of trusses. So just to finish off, let's go back to the binary perspective. So you can ask the following question: well, a truss is defined as a abelian heap with an associative multiplication satisfying a natural distributive law. However, we know that an abelian heap gives rise to a family of groups. So we can reduce the problem, but we can reduce the Turner operation to a binary operation. And we can ask what kind of distributive laws we will get in there. So I would call it a binary perspective. On trusses. Okay, so given a truss T, select an element, E and T. And we can define operations T to T, sigma R and sigma L. Sigma L of A is A dot E. Sigma R of A is E dot A. That's multiplication from the left or from the right. And we just note that sigma L of E is the same as sigma R of E because they are both E squared. Now we can convert the heap to a retract group G of T E. So E is a neutral element. And I will skip writing the index. A plus B is A E B. Minus A is E A E. Then A dot B plus C, what kind of distributivity we get with respect to this addition? A dot B plus C is A dot B E C, A dot B, A dot E, A dot C. But A dot E, by the definition, this is sigma L of A dot C. And then if I convert it again to the binary operation, then it's A dot B minus sigma L of A plus A dot C. And similarly, A plus B dot C will be A dot C minus sigma R of C plus B dot C. So one can think about a truss as a system T, a set, plus, so that's making abelian group, multiplication, and sigma R, sigma L functions with sigma L of A defined as, so remember the neutral element is just a 0 for the multiplication, so it's A dot 0 and sigma R of A 0 dot A. And then if sigma L of A is equal to sigma R of A is equal to 0, then we have a ring. And if sigma L of A is equal to sigma R of A is equal to identity, so it's A, it's an identity map, then we have a brace. And in this sense, the trusses interpolate between braces and rings. On one hand, we have a trivial correction to the distributive law, and that's the case of the ring. On the other hand, we preserve everything. We don't change anything. So it's an identity map, and then we have a brace. And I think my time is up. So thank you very much for your attention. And if you have any questions, then please ask.
Okay, yeah, thank you so much, Professor, for the talk. It's very interesting. We will have a question and answer session. You may send the question on the chat, or maybe you can also turn on your microphone and ask to Professor directly. Okay. Let's see. Oh, this one. Oh, 3 questions.
Okay, so I will read out the questions.
Okay.
So is it possible to have a truss that when retracted back to binary operation, we have a ring and also brace at the same time? Well, it is possible, but that's the only trivial case. That's just one element set, because in the if we have a brace, then the necessary condition is that 0 is equal to 1. So to have both brace and truss, brace and ring, we need, well, the situation when 0 is equal to multiplicative identity, which is only the trivial ring. Now, the second question is, you mentioned about Yang-Baxter equations, one of the motivations, the introduction of trusses. Other than that, is there any possible application of trusses in other fields? So my own motivation, it started with the understanding the relationship between braces and rings, but one of the nice applications is in the affine geometry. So whenever you have if you think about this example of trusses coming from affine spaces, whenever you have a linear algebra, the algebra of vector spaces, when you study operations on vector spaces and multiplication and so on, you end up with rings. But if you replace them by affine spaces, then you end up with trusses. So that's one of the applications. The applications can be done arise also from geometry. So one of the recent observations that we've made with my colleagues is that if we have say an elliptic curve, and on the elliptic curve you can define a Turner operation, which turns out to be a heap operation, and all the endomorphisms of an elliptic curve, so the rational functions from elliptic curve to itself, form a truss. So there is a natural application to geometry. Another example is if you look at the complex torus, then a complex torus is just Cn divided by a finite subgroup, and this gives you by the discrete subgroup, and since this is a group divided by the subgroup, we get a natural group and heap operation. And if you look at the analytic homomorphisms on the torus from the torus to itself, then again they will form a truss, not a ring but a truss. So these are geometric, if you like, applications. Now with the ideal, well, I didn't get to the ideals, so no. So the ideals have to be defined slightly differently, so we call them paragons. And what would be a natural definition of an ideal was in some set corresponding to, well, let's go back to the end of my the first part of the seminar, when I said a bit more about the kernel relation. So the fundamental for the definition of a kernel or an ideal in a ring is that the quotient by the ideal of the ring is a kernel relation. The relation induced by the ideal is a kernel relation. So now, from the point of view of heaps, the kernel relation for heaps will correspond to those relative kernels or inverse images of a chosen element in the image of F. Now, when we move to trusses, there's this additional operation, multiplication. We would like to have, we look at the kernel relation. So in particular, it will be also the kernel relation for heaps. So it will correspond to the relative kernel, but it has to have additional property to preserve the multiplication. And this property, I can write it down what it comes out, because it is the following. So it does not give you an ideal property. It's something that is closed under multiplication from left and right, but the paragon property. So P will be a paragon in T if it has a property that for all A in T, PQ in P, A P, A Q Q is in P, and PA, QA Q is in P. for all A, T, P, and Q. And in fact, if it's this can be replaced by there exists P and Q. Actually, there exists Q, such that this is true for all A and for all P. So in particular, if you have just a usual sort of ideal property that AP is an element of P, then you can take for Q a P again, and then it will you have an element of P, an element of P, and element of P. So I should say this is a subheap. And this will be automatically satisfied, but not the other way around. So this property does not imply that A times P is an element of P. So the definition of an ideal has to be modified. And yes, this property, the paragon property, indeed corresponds exactly to the kernel relation, and it gives a quotient. So the quotient T by P, so by the relation corresponding to P, is a truss again. And every truss, and whenever you have a surjective mapping from one truss to another, you will find that there is a corresponding paragon, just as in the usual ring here. Any other questions?
Okay. Yeah, there's another question from Ningjo Harto Farida. She asked, I want to ask, what do you think about the future of research about trusses, and what can we observe further? It's interesting.
Okay, so it depends how much time you have. So I can talk a lot. Yeah. No, there are a lot of things that can be done. In a way, it's an open book. You just if you think about problems coming from ring theory, or the problems in ring theory, then immediately you can counterparts in trusses. So one of the things that I mentioned this, but there is a module theory for trusses. So you have modules of trusses. You have, but then one can realize that actually, again, the definition of a module has to be slightly modified. And then when you have modules, then there are a lot of questions that you can ask. So for example, how you can classify trusses by using some kind of Morita theory. So the equivalences between categories of modules, the representations of modules. You can look at the classification of trusses. That's another problem, which is as open as and gives so many possibilities as the classification of rings, as I mentioned, on a given abelian group, or classification of groups which give. So as I said, on every abelian group, you will have these two trusses, or classes of equivalence classes of trusses. So then you can ask what kind of groups would have only these? Are they exactly the same as we would have for rings, for the nil groups? Probably not. So there are, this classification leads to the classification of problems in group theory. So there are, it depends what you want to do. There are a lot of things that can be done.
Thank you, Professor.
You're welcome.
It's very interesting.
Okay, thank you so much. Yeah, any other questions, participants? So yeah, there are a lot of things to do in this topic actually. Maybe I also curious about the possibility for us to construct a graph from a truss. It's also possible, right? Because yeah, it's like in the ring theory, we can make a graph from a ring, like zero divisor ring, and etc.
Yeah. I guess I don't know much about graph theory, so it's but I am pretty sure that you can. But when you start doing this, you will see that there are, I mean, how can I put it? On one hand, trusses are very similar to rings. So you think, well, okay, there are a lot of things open in ring theory that can be studied, transferred to trusses. But then when you start looking, then you realize, well, you have a lot of new ideas. Because a lot of ideas which are used in ring theory. So, for example, if you have ideas of nilpotent rings, so there are rings when you look at an ideal and you multiply, and at the end you get something trivial. And then, if you look at the trusses, what does it mean trivial? In a ring, it's obvious you will get zero ideal. But how about trusses? What kind of paragons you can get, and you can. So it opens a lot of possibilities, and I don't know what kind of problems you have in mind corresponding to graph theory, but if you, I mean, it's tempting to start doing something, and then you realize, well, there's something actually more, which is not a bad thing. It's on the contrary, it's a good thing, because you discover that there are a lot of new points of view on something which is already in the domain of rings, or in this case, graphs and rings.
Yeah, okay, Professor. And yeah, there's another question in the chat box from Nikan.
Okay, coring and weak coring is a generalization of coalgebra. Is it probably that we can construct another generalization structure of coalgebras of comodules from heaps and trusses? Okay, so there is there are quite a few papers on they are called quantum torsors. So if you look at the topic of quantum torsors, there's a papers by Grunspan and Schauenburg. Then you will see that they study Turner operations, or the extent quantum groups or Hopf algebras to heaps. So rather than having a binary operation, there is a linearized version of the Turner operation. So yes, it's coalgebras have been extended to heaps in this sense, but for trusses, I don't think, well, in my paper I wrote about Hopf trusses a bit, so there is an attempt to do this, but not in the ternary setup. This was done from the binary perspective, not from the ternary perspective. So categorically, from the categorical point of view, it's a different approach. So it's an interesting area.
Thank you, Prof. It's nice.
Welcome.
Yes.
Okay, thank you so much. And yeah, we have 5 or 10 minutes left. So if there is another questions, yeah, you can send it in the chat box. And yeah, while waiting, I also curious about the last question from Siti about the paragon and ideal. I think about the ideal and paragon in trusses, does the notion of paragon comes from like the flexibility of truss to be a brace and a ring? So let's make that.
Yes, it does. Yes, it does.
Okay.
Yeah, that definitely it does come from this, because you see if you think about brace, then 0 is equal to 1 in the brace. And then if you think about traditional way of the ideal in the ring as something which is closed under it's a subgroup closed under the multiplication by all elements of the ring, then since it's a subgroup, it must contain 0. But if it contains 0, it contains also 1, because 0 is equal to 1. And if you multiply by 1, it means that you immediately, just like in the ring, you would have an ideal which contains the identity of the ring is the whole ring. So from the point of braces, the traditional definition of ideal doesn't make sense, because you don't have anything there, just the whole brace. But this definition, that's actually, if you reduce it to the word of braces, this is how ideals are defined in braces. If you translate what they do to the ternary situation, that's exactly how the ideals are defined in braces. Its modification comes naturally from the brace theory.
Okay, well, that's very interesting. The flexibility of trust to be a brace and also a ring.
I mean, it's if you think about the most the best case in the rings, the nicest rings, the fields, they don't have ideals.
Yeah.
But it's either 0
or itself,
or the whole thing. And in braces, it's even in this sense, ideas in this sense, it's even worse, because there's no 0 idea.
Yeah.
Because everything immediately when you have 0 inside, and multiplying by 0 is it does not give 0, but the element itself. So you have the whole thing immediately inside.
Oh, yeah. It's very interesting. Okay. Yeah. So participants, do you have any other questions? Okay. Well, I think that's all for the lecture for the second session. Yeah, actually, it is the last session of this algebra seminar too. Again, thank you very much, Professor Tomasz Brzezinski. It's really nice to have you in this seminar. We are very happy to have you. Yeah. But before we finish this algebra seminar, we actually have we have a virtual gift, let's say, for you. Yeah, because it is conducted in virtual seminar, so we have a virtual gift for you. So wait a minute, maybe operator, can you share the screen? Okay. So yeah, this one, this virtual gift will be given by the vice chairman of the committee of this event, which is Ning Jawharatul Farida. So please.
Okay, thank you so much, Professor. Yeah, this is a little gift from us. I hope you will be happy with this. On behalf of the Algebra Research Group of the Faculty of Mathematics and Natural Sciences, ITB, please accept this gift as a token of our appreciation for your talk. It was a pleasure. It was a pleasure to have you with us today, and we hope we can continue our collaboration in the future. And we hope
I would be very happy to continue collaboration. I already had some contacts with Fitri, but you are welcome to further discussions and collaborations.
Yeah, thank you so much.
Okay, thank you very much.
Okay, yeah, thank you so much. Maybe after this seminar, we will send this illustration for you. It is illustrated by our student. Actually, he's an undergraduate student. So yeah, hope you like it.
I do. Yes. Thank you.
Yeah. Okay. So yeah, I actually have read a quote said that better than 1,000 days of diligent study is one day with a great teacher. So let us appreciate our lecture today with a great teacher, which is Professor Tomasz Brzezinski. Thank you so much. Okay.
Thank you very much. Thank you.
Yeah. So yeah, thank you very much, Professor. Hopefully, this event can raise the interest in process theory, especially in our research group. Maybe what
I would be very happy. So
yeah, but maybe we can conduct a collaborative work or research or anything, or perhaps next time we can invite you in person to Indonesia. It would be very interesting.
It would be very nice. Yes.
Yeah. Have you been to Indonesia before?
No, I haven't.
No. Oh, so yeah, maybe next time we can invite you to Indonesia, to Bandung. Yeah. Okay. Thank you so much, Professor, again.
Thank you very much. Thank you. Thank you very much for your invitation and the very kind gifts and very nice reception. So it's nice to talk to an interested audience.
Okay, yeah. So yeah, participants, we have arrived at the end of the third day of the algebra seminar, and it is also marks the end of the algebra seminar 2022. So we would like again to deliver a big thanks to our today's lecturer, Professor Brzezinski, and of course to all the participants. We hope that you all enjoy and all of the sessions delivered today and also gain new knowledge. So I am Fitri. Good afternoon and good morning, and see you when I see you again. Thank you so much. Assalamualaikum
Thank you.
warahmatullahi wabarakatuh.
Bye.
Thank you.